By this point, we did do a lot of differentiation and integration rules. Okay? And I believe it's time, with the differentiation rules that we've learned so far, to learn about a cheat method. We're going to call it a hack method of finding limits, and that is known as L'Hopital's rule. L'Hopital's rule. Okay? And L'Hopital's rule is super useful. Okay? In that it can be used to find a lot of major limits. Okay? A lot of them. Now, what L'Hopital's rule basically says that if you have a limit as x approaches 0 of f of x over g of x. Okay, so what L'Hopital's rule basically says is that as x approaches not just 0, but any number a, or x approaches infinity, or negative infinity, it depends. As x approaches infinity, negative infinity, or just a constant of a ratio of two functions, f of x over g of x. And that is equal to either 0 over 0 or infinity over infinity. Okay? If it's infinity over infinity, negative infinity over infinity, or negative infinity over negative infinity. Or basically, if it approaches either 0 over 0 or infinity over infinity, okay, or any of these, and if this equals 0 over 0 or infinity over infinity, then the limit as x approaches a of f of x over g of x equals the limit as x approaches a of f prime of x over g prime of x. Okay? So this, of course, is provable, but, I won't do it right now. Okay? So you can always prove this and see if you can prove this. Okay? So, but this is basically what L'Hopital's rule says, and it's very useful for evaluating limits that can't really be easily evaluated algebraically. So let's take, for example, the limit as x approaches infinity of ln of x over x. Now, if we basically study both of these functions, as ln of x approaches infinity, as x approaches infinity, ln of x also approaches infinity. And obviously the same goes for the denominators. You have infinity over infinity, which means you could do L'Hopital's rule. Okay? So if we find the derivative of the top function, remember, you do not use the quotient rule. So you're not finding the derivative of this, but you're finding the derivative of the top function over the derivative of the bottom function. That's 1. So the limit as x approaches infinity of 1 over x, and that equals 0. Okay? Now, let's say you had the limit as x approaches infinity of x over e to the x. Okay? Now, over here, you get infinity over infinity again. So you can easily differentiate this, the top and the bottom functions, okay? And that also gets you 0. So now you can see how easy it kind of is, okay? However, it is, excuse me, it is not always this easy, okay? Because this is not a cure-all. It's not a magical limit solver, okay? Let's look at some other ways that a function can be indeterminate, a form can be indeterminate. So you have 0 over 0, infinity over infinity. Those are good ones, okay? Now here's some bad ones. You need to change these, okay? 0 times infinity, infinity minus infinity, okay? That is also a no bueno. 1 to the infinitieth power, 1 to the infinitieth power, 0 to the 0. While many people think it's just 1, okay? While many people think it's 1, the actual limit is indeterminate. So 1 to the infinity, 0 times infinities, infinity minus infinity, and infinity to the 0th power. They're all indeterminate forms they're all indeterminate, and you need to change the x ones into these two so you can use L'Hopital's rule. So let's look at excuse me. Let's look at an example. Okay? So let us look at an example. Let's find the limit as x approaches infinity of e to the negative x times the square root of x. Now what does that equal? So if we substitute and write in, well, as x approaches infinity, e to the negative x approaches 0. However, the right term, root x, approaches infinity, so you have 0 times infinity, which is an indeterminate form. However, you can't use L'Hopital's rule because that is not 0 over 0 or infinity over infinity. So what you have to do is convert it into a form where it yields either one of these terms. And there's an easy conversion that you should immediately see. That e to the negative x can be turned into e to the x into a denominator. And now I have infinity over infinity, which means you can use L'Hopital's rule. So you have 1 over 2 root x, okay, over e to the x. So you have 1 over 2 e to the x root x. Okay, and that is obviously equal to 0. So that is a no-brainer. It is 0. Okay? So what can you do? There's a lot of different ways that you can solve limits, okay? And remember the log. Yep, it's biting back again. Okay? Let's try to find the limit as x approaches infinity of 1 plus 1 over x to the x power, which might seem familiar, but we'll use L'Hopital's rule to prove it. So we're going to assume that this limit exists. It's an assumption. Now, y equals this limit. So what you can do is take the ln of both sides. So if we were to evaluate it directly, you have 1 plus 1 over infinity. Okay, that's 0. That approaches 0. To the infinitieth power. So this goes to 1 to the infinity, which is indeterminate. So you have to find a way to fit it. Okay? You have to find a way to fit it. And the way to fit it is to take ln. So ln of this is 1 over x to the x power. Now, there is a really special thing you can do, is that you can bring ln inside the limit. And there's one reason for that. The ln function does not break. And if the ln function does not break, it will not affect the limit by putting it inside. Okay? So what you can do now is, let's see if we can evaluate. Before we do that, we can bring this over here. So ln of y equals the limit as x approaches infinity of x times ln of 1 plus 1 over x. So we have 0 times infinity. However, let's see if we can bring it into a form in which we get either 0 over 0 or infinity over infinity. Now, ln we can't really bring to the bottom, okay? So we'll have to keep that on the top, okay? There's no inverse ln. So the only way we can get 0 over 0, infinity over infinity, is that we bring x to the bottom. And the only way to do that is to rewrite this function as ln of 1 plus 1 over x over 1 over x. And now I can see we have 0 over 0. So L'Hopital's rule will suffice. And if you were to simplify it, you'd basically be finding the limit as x over approaches infinity of 1 over 1 plus 1 over x. So that limit is equal to 1. But we have to remember this ln of y over here. And by taking e and e, you get y equals e. So this limit, we just show the limit as x approaches infinity of 1 plus 1 over x to the x power is in fact equal to e. In fact, that is equal to e. And now you can see that you can see how useful this rule is, okay, in the sense that it basically solves a lot of your limit problems, your limit issues, because if you just put it in a certain form, then you don't really have to do much, okay? You just take the derivatives at the top and the bottom. Now, you can use L'Hopital's rule more than once. I'm going to show that in this little proof exercise. So prove that the limit as x approaches infinity of x to the n over e to the x equals 0 for all positive integers n. So n is greater than 0, okay? That means n is greater than 0. Now, what do we do? Okay? What do we do? Now, what we can do is, as x approaches infinity, we get infinity over infinity, okay? If we were to evaluate this limit by substitution, you see that the numerator approaches infinity and the denominator approaches infinity. So we have an indeterminate form. So what we can do is apply L'Hopital's rule more than once. So we have n times x to the n minus 1 over e to the x. But this also results in infinity over infinity. So we do this again. So we have n times n minus 1 times x to the n minus 2 over e to the x. And that also gets to infinity over infinity. And you can do the limit. So we use L'Hopital's rule yet again. And we get n times n minus 1 times n minus 2 times x to the n minus 3 over e to the x. And that again gets infinity over infinity. And you keep on going on until you take the nth derivative. You apply L'Hopital's rule for the nth time. And you can start to see a little pattern here. Okay? So the nth time, you would get n times n minus 1 times n minus 2 all the way to 2 and 1 over e to the x. Or the limit as x approaches infinity of n factorial over e to the x. Now this is a constant over e to the x. Okay? So this means that you can easily see that this would approach 0. Okay, you have a constant over e to the x. So that means you can see quite easily that it will approach 0. So we've just proven the fact that this is equal to 0. And what's interesting about this is that you can use L'Hopital's rule as many times as you need in order to get your solution. There's no requirement of using it only once. You can use it, as in this example, you can use it as many times as you want, as long as it meets the conditions of 0 over 0, infinity over infinity. And, differentiable, because you're taking derivatives, okay? So as long as it meets these two conditions, use as many times as you need, okay? And at some point, it will give you your limit. Thanks for watching. If you have any questions, please make sure to comment, like this video, and share it. And keep tuning in for more videos. Thanks for watching.